All right, so we're talking about the chain rule today, 2.6. Yesterday we talked about the quotient rule. Before that was the product rule. We've also done constant multiple rules, power rules, sum difference rules, and constant rule. Did I mention that? I think I did. So we've gotten a lot of derivative rules kind of under our belt here now, and we're going to be working on those throughout the course. You'll see those come up in pretty much every question that you do. The chain rule is, I think, the last main rule that we're going to learn today. Arguably, it's the most difficult, but I think that if we take a look at this very carefully and think it through, it's not going to be that hard, okay? So the chain rule would be used for a question like this. Now, before I get into what the chain rule is or why we would use it, let's just review what we've done before. So we have done, and you don't have to write this down, but we've done the sum and difference rule, right? Let's do plus or minus here. And that is you take the derivative of each function that's added or subtracted, and you add or subtract the individual derivative. So that's the sum difference rules, right? We've also done the product rule. So f times g, right? We just got finished doing that. So that's derivative of the first times the second, plus, it's always plus, the first times the derivative of the second. So this is sum difference, sum diff, this is product rule, okay? And we just learned the quotient rule. So that's f over g. If we're trying to find a derivative of a rational function, that's the derivative of the top times the bottom, and then it's minus the top times the derivative of the bottom over the bottom squared. So this is quotient rule, okay? So if you take a look at the terms that are added and subtracted, you can just take the derivative and then add or subtract the derivatives. If they're multiplied, it gets a little more complicated. If they're divided, it gets a little bit more complicated. Now, this is obviously a product of functions. This is a division of functions. What the chain rule helps us to find the derivative of is a situation where we have a composition of functions, okay? A composition. So I'm going to erase this stuff here now. It's just a bit of review. So a composition of functions. Now, you might remember that a composition of functions would be like if we had g of x inside of f of x. Okay? So we've dealt with adding, subtracting, we've dealt with multiplying, we've dealt with dividing. Now we're dealing with composition of function, where we have a function within a function. Okay? And I'm just going to change the color of this just to be real fancy like. What color should we pick? Pink? Pink? No, that might not look very good. Orange?
Neon green.
What? Neon green? Right here? I don't know if that's going to show up very well.
I like it.
That shows up okay. All right. So neon green. Okay. So there's often a function within a function. Now, we're going to get to the point where there's a function within a function within a function. It's like an onion. Like layers of an onion. What's that? The Shrek?
Yeah.
Onion. Donkey. Oh, he's like an onion. I can't do the voices now. But anyway, so Shrek's like an onion or something. Donkey, get out of my swamp. Get out of my swamp, donkey. Something like that. I know I look like Shrek. Look at it. I'm even wearing green today. Nervous laughter. Okay, good, good. Yeah, don't laugh too hard. You'll offend me, right? Good job. Okay, good job. What do you mean, is that an onion? Of course it's an onion. What are you talking about? Is that an onion? What are you talking about? Of course it's an onion. You see, it's cut.
It's like a ham.
It looks like a what? A yam?
It's like a yam.
A yam?
What yams have you been eating? Like a tree trunk. Oh, yeah. Or like a fish.
That's brilliant. It's chopped onion. It's the piece of onion that's gone.
It looks like it's staring at me. It is. It is.
Oh, really? Okay. Are you ready for this?
Oh, wow. I'm not sure how I feel. Yeah, let's not. That's why I imagine Julius.
Look at this. Okay, back to calculus. Sorry, I'm not sure. You guys throw me off. Okay, here we go. And onions. Okay. So why do I draw a picture of a beautiful onion there? Why is this so fantastic, and why did I draw this? Because when you're doing the chain rule, you have to address the outside layer of the onion, and then you have to address the subsequent inner layers. So remember how in the product rule we took the derivative of the first and then multiplied it by the regular old second. Then we added the first times the derivative of the regular old second. We had to take the derivative of both functions, but we couldn't just take them right away. We had to, there's a process. Same thing here. We take the derivative of the outer layer first, the outer blue layer in this onion. Okay, I'm not sure what a blue layer means. Some kind of tragic bacterial infection there. And then we move into the inner layer, okay? And if there's only 2 layers, there we go. Do outer layer first, and then inner layer. And just like in the product rule, we take the derivative of the outer layer, and then we leave the inner layer alone at first. And then we take the derivative of the inner layer next, okay? So, outer function, I'm going to always sort of speak of outer function, okay? So the outer function is f of x, okay, or f of u, okay? F of u. Calculus textbooks everywhere use f, the function with the variable u in there. I don't know why. It's so inappropriate. F of u. Anyways, when I say that, students are offended sometimes. Anyways, I'm not saying, there's an of in between, okay? Okay, f of u, okay? So the outer function is f, and we'll call the inner function u. So the inner, then, u are the inner function, okay? U are the inner function, right? This is a separate function. Think of it that way if you want. And in Leibniz notation, that's often what they'll do. And I'll show you Leibniz notation. It's the u is the inner function. Okay. So how do we deal with this? How do we work on the layers? What we do is, if we're going to find the derivative of this f of x, what we do is we find the derivative of the outer function first, and we leave the inner function inside there. We leave it alone. So we address the outer layer first, and then we multiply. Okay, this is the first time we've multiplied. Product we add, quotient we subtract, chain rule we multiply by the derivative of the inside function. All right, and that's it. Now, if there are more layers, we'll deal with that later. But it's easy. You just keep multiplying by the layers, the subsequent inner layers of the function. So the trick is identifying the outer and inner functions. Sometimes that's the trick. Okay, and we'll get to this example in a second. I'll do this example, but let me just outline what I've said so far. Okay, now you can copy down as much or as little of this as you want. The chain rule here, this is a bit of a combination of Leibniz and Newton notation. I don't know why they do this, but anyways, it'd be like, the derivative of this, if they're being consistent, I guess, I don't know. The derivative of a composed function or composite function is the derivative of the outer function multiplied by the derivative of the inner function, okay? Another way to write that composition is f circle g, okay? That's another way to write it, but we usually write it like this, with the g of x inside the f of x, okay? So derivative of the outer layer times the derivative of the inner layer. I mentioned Leibniz notation here. In a sense, this is actually simpler for the chain rule, isn't it? And this is where Leibniz notation is used quite heavily in calculus, is in the chain rule, because we can kind of see, and let me just explain this, maybe a little more detail here. So zoom in a bit. So we have the derivative of y with respect to x. So we're taking the derivative of the function y, whatever that is, and what we're doing is we're taking the derivative of y only with respect to u. Now, what is u? I mentioned u is the inner function. Okay, what's the inner function? U is. Right? It's bad English, but and so what we do is we take the derivative of the outer function, and we leave the inner function alone in there. So with respect to whatever the inner function is, the inner function is the variable kind of thing, what we take with respect to, and then we multiply by the derivative of the inner function with respect to x. So when all is said and done, this is a multiplication, and we have du and du canceling out, sort of dividing out, and we end up with dy over dx. Okay, so in this sense, I guess people would argue that Leibniz notation is much easier to envision and to work with than this one. Okay, people kind of get confused with this one, but it's the outer function derivative multiplied by the inner function derivative. And if you remember that, you're going to be fine. So, as promised, let's get back to this example right here, and let's identify what is the outer function and inner function, and then we'll actually take the derivative. So you can copy that down if you haven't already. And we're going to find f prime of x. So let's first of all identify what the outer function is. So f of x, the outer function, would be what? In blue. So I will highlight in blue. Well, we have two things going on here. We have the square root on the outside. That is the outermost sort of function. Think about the outermost function. What's on the outside? The square root is on the outside. And so really, we have root x is our outside function. The square root of something. And if you'd like to change this to u, that's great. Let's do that for now, because that's what we said. So you can change that if you want to. Apologize for writing that x. So f of u is square root of u. You see that's the square root function? What about u? So what is u actually equal to? Well, u is the inside function, and what's inside the square root is 2x squared plus 3. So 2x squared plus 3 is the inside function. Or f of x. See the textbook will tell you what would f of x be and what would g of x be. That's the wording that's going to use. So we'll do that as well. But if you think about f of u and then what is u, according to Leibniz here, then we have an outer function and inner function. Okay? Is everyone okay with that, identifying the functions? Okay? Usually it's like some kind of operation, maybe a power to the exponent of, or some kind of quotient situation. And then inside you'll see an expression usually that is inside of another larger sort of looking function. Okay, so the derivative now. Let's do the derivative, f prime of x. So what we do is we take the derivative of the outside function. So I'm going to treat this, I'm going to rewrite this before I take the derivative. Let's rewrite a square root is usually best if we rewrite that as a fractional exponent. Now, why would we do that? Because I know how to take the derivative, and let me highlight this in blue again. So here it is. See, this is the outside function here with the fractional exponent, same thing. I know how to do that. So I take the 1/2 and I bring it down. I'm using the power rule. 1/2. And this, again, I leave this alone for the first round here. I'm only dealing with the derivative of this outside function. So this stays as 2x squared plus 3. You leave it alone. It's like our original function there. You see? F prime of x, and then g of x stays inside alone, untouched. Okay? And this is negative 1/2 because I subtract 1 from 1/2. Good. Not done. Not done because there's a significant portion of this question that I have not touched yet. I have not taken the derivative of that, and you have to take the derivative of every part in the proper order. So what's the derivative now of 2x squared plus 3? It is 4x. Okay. So that is the chain rule, unsimplified. We've done the chain rule, and this is multiplied, of course. Okay? So that is unsimplified round 1. I'll pause there. I'm going to simplify that in a second. I'm going to simplify this. Write it the way most of the time you should write it. But if you were asked to take the derivative and do not simplify on a test, that's what you would leave. That's your answer right there. Can someone tell me if they have a problem with that or have any questions about this? Yes? Why is it a negative 1/2? Because in the power rule, remember the power rule? So you have to subtract 1 from this exponent. So that's a 1/2 minus 2 over 2. So it'd be negative 1 over 2. Sorry? No, you have to find the derivative of the outer function first, then multiply by the derivative of the inner function. So you do have to take the derivative of the outer function. Very important. That's the very first thing. This is the derivative of the outer function right here. Okay? Now, with respect to u, which u is the inside function. So you take the derivative of the outside part, and you're basically treating this like a variable. So watch this, okay? This is like a variable u, right? It's u. So I leave u alone. I'm going to leave you alone, okay, everyone? Not going to bother you. You leave u alone in there, and you take the derivative of the outside part, just like it was a separate function. And then you multiply by the derivative of u. This is u prime here, right? That's u prime right here. Okay, does that make sense? Does that help? Maybe? Okay. All right, so simplified, of course, we see a couple things right off the bat that we should do. One is combine the 4 times 1/2. That's just going to be 2. Okay, and this negative exponent brings this whole thing down to the denominator, and to make it a positive 1/2. Okay, and so the x also is up on the numerator, and so we're going to have 2x squared plus 3 to the positive 1/2 down here, which actually translates to square root. So that would be your simplified. Okay, and if you had 2x squared plus 3 to the power of 1/2, I wouldn't fault you on that one, but most of the time you're going to want the square roots in there as the final version. Okay, good? You like it? You like it, you love it, you want some more of it? Classic song. It's a classic country song. All right. So what do we got? This looks like what we got here on this is the example. This is what we got? Yeah? Nice. Okay. So check this out. Here's another way of writing the exact same question. You see? U, inner function. Y is root u. Here's the outer function, square root. Leibniz notation. Let's take the derivative of this first, and then multiply by the derivative of this second. Okay, so there's the solution doing it that way. Derivative of y is 1/2, all right, u to the negative 1/2, that's what this is, times the derivative of u is 4x. Now substitute u into the equation and simplify. All right. Next, let's, let me highlight this. This is what we did as well. This looks like it's totally different, but it's not. This is just what we did. So obviously with the chain rule, you can combine other rules, right? You can combine product rule, quotient rule, along with the chain rule. It's going to get a little bit more complicated. But here I did an example, this one, where we combined the power rule with the chain rule. So the chain, think about a linking of a chain. You're just linking functions, the derivative of functions together. And if we can make sense of this one here, so if we have an outside function that is an exponential function like that, like has a exponent there, then we do the power rule and leave the inside function alone, and then multiply by the inside function. That's what we just did. Okay, so they take the time and space to show you that this can always happen as well. So anything with a power, whether it's fractional or otherwise. Okay, write this example down. Let's do example number 3. Okay, this one is kind of set up as using Leibniz notation, so let's go ahead and jump into that. Remember, dy dx is dy du times du dx. Again, what that is saying is take the outside overall y function right here and differentiate it with respect to u first. So that is the inside function. Then you differentiate the inside function with respect to x, your variable, and you end up getting dy dx. So first of all, what is u, the inside function? What do you suppose, what looks to be the inside function here versus the outside function? What do you think u is here in this example? Sorry? Nice and loud.
Squared minus x plus 2.
Exactly. X squared minus x plus 2. That is the inside function. You don't want to say like something like x squared or just x. Say, oh, I see, x is inside, another function that has x squared. No, it's not inside. It's just part of the most basic rock bottom foundational sort of function in this expression. Okay. So yeah, that's u. Now, what would y technically be? Well, I guess we have y there. Let's write y in terms of u, though. In terms of u. So what is y written in terms of u? Very good. U to the power of 8. Yes. Okay, you guys are getting it. So now we'll take dy, dy with respect to du. Let's just do this one first, okay? Let's just focus on this first. So what is dy with respect to du? Well, we're taking the derivative of y with respect to u. U is kind of like the inside variable, and of course it is here in this expression. So this is going to be, use our power rule, 8 u to the 7. That's dy du. It's the derivative of the outside function with respect to just the u. Now what is du? Du dx. So that is the derivative of u with respect to x. Well, I focus on this. Here's the variable x. So that is 2x minus 1. So I have 8u to the 7 times 2x to the minus 1. And I do not want to leave u at all in my final answer because I am looking for the derivative with respect to x only. So I should substitute what I have here. 8 times x squared minus x plus 2 times 2x minus 1. There you go. And you can stop right there. Don't have to expand it. Leave it in factored form is fine. Factored form is fine. Okay. Now, I know you're just learning this, so again, I don't want to confuse you by doing, Leibniz notation as well as Newton notation, get you all confused. I don't think you will be confused. But let me do this the other way, where we're not identifying the u. And this is the way you probably will default to be doing it as you move forward, okay? This is the way that I do it. I don't really identify u and identify y and then do the substitution later. I don't really do that, okay? You don't really have to. Let's do it like we're going to find straight y prime, okay? You have noticed that we have an outside function, I'll highlight it in blue, that is like blah to the power of 8, right? Blah, whatever. U, blah, blob, okay? It's just a steaming blob right here, okay? Blob to the power of 8. So that's our outside function. And I'm going to leave everything inside alone for now, and I'm going to do chain rule. So 8 times x squared minus x plus 2 to the power of 7. So that's my first round of taking the derivative of the outside. And then I'm going to multiply the derivative of the inside, which is going to be highlighted in red here, the inside function. So times the derivative of the inside would be multiplied by 2x minus 1. Boom, done. So obviously this is why I go with this method. But this might help some of you understand sort of what we're doing with the outside-inside function. I don't know. It's a little more work, and I'm not going to require this on the left here. D, y, du. Okay? Question? Yep.
Did you forgot to add the exponent of 7 on the left side?
Oh, on the left side, yes, you're right. I did not add this, or it disappeared, one of the two. Things are randomly disappearing, but yes, I might have forgotten that. That should be there, correct. Yeah, from right here. Good, anything else? Any questions or no? Okay. All right, let's do this one. This is super small font here. Whoa. Okay, it gets out of control pretty quick, doesn't it? All right, so find the derivative of the function f of x equals x squared plus 1 cubed times 2 minus 3x to the power of 4. And we're going to say do not simplify, okay? Simplify. Okay, so what you want to notice here is that we have a combination of 3 things going on. We have a combination of power rule with this exponent, chain rule with finding the derivative of this whole thing here, and product rule because we're multiplying 2 distinct functions. So we've got several rules in action at once here, okay? So this is where it gets tricky, okay? We're not isolating just one rule at a time or chain rule and power rule, which kind of like is, that's pretty easy. Now we've got product rule on the large scale. When we find the derivative of one of the functions that we're multiplying, we have to do chain rule in there. So we have to do power rule and chain rule, okay? So there's multiple layers here of this one. All right, so let's take this one slowly and carefully. I do see that this is ultimately a product, right? One function times another. So I am going to do product rule. I have to keep in mind product rule. And so that is f times g prime is f prime g plus f g prime. Okay, obviously large scale. Now, drilling down on that, I see that f prime is going to be the derivative of this function. Wow, so this is a composition of functions. So I'm going to have to do chain rule in here. See that? Chain here, and chain over here with the g prime. Yes? Sort of? Okay, let's let's push through. Again, it's practice, 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 and exposure. So let's do so f prime of x here. This is this here is going to be the derivative of the first times the second. So the derivative of the first is what we'll focus on first, and that's going to be 3 x squared plus 1 to the power of 2, using the power rule, along with now the chain rule times 2x. So f prime in this product rule is the derivative of this, which is this. You with me? Or have any questions?
Yeah.
Where'd the 2x come from?
Yeah.
The derivative of the inside, 2x.
Oh.
Yeah. So outside function is this thing cubed. So I did that. So 3, this thing to the 2, times now, remember, I'm not done taking the derivative of this because I haven't taken the derivative of this inside part yet. So I have to take the derivative of that as well, and that comes as a multiplication. So 2x is derivative of x squared plus 1. Good question. Thank you for asking. Anything else then? No? All right. Okay, let's move on. G, well, G's easy. Let's just do 2 minus 3x to the 4. We leave it alone. You see, product rule says we leave G alone. I'm just going to show that as a multiplication of G. Fine. Plus f alone. Leave it alone. What was f again? I've messed it up over here. It is x squared plus 1 to the power of 3. Awesome. Now I do g prime. So now I got to focus on the derivative of this, which is going to include the chain rule. So times 4, the exponent brought down, leave alone the inside for now, and then this is to the power of 3. Now I take care of the derivative of the inside part by multiplying by the derivative of this expression, which is nice and loud. No one knows? -3, yes, multiplied by -3. Good so far? Okay. Now we've taken care of everything. Remember, here is g prime, okay, the derivative of this, which is right here. Okay, that's the chain rule parts that you should make sure you've highlighted, that you know about. And then of course the obvious larger picture is this is product rule. Prod. So that's the whole picture, is the product rule. Derivative of the first times the second, plus the first times the derivative of the second. So do not simplify, that's where we end, right there. We're done. Simplifying, what would simplifying entail? Well, simplifying would entail, first of all, you've got this in largely factored form, right? So don't be expanding, don't take an hour to expand all these things to the, a binomial to the power of 7. Don't expand it. Just don't do it. If there's common factors though, you should pull those out and factor. So is there a common factor here? Yep, there are common factors all over the place. I have a common factor of x squared plus 1 to the power of 2. That is common to both sides. Remember, it's separated by the plus. So this is one large term, this is one large term. This is a common factor right here. So I can take 2 of these out and pull them out front. Then I look along here and I've got 2 minus 3x. That shows in both. And I have at least 3. So 2 minus 3x to the power of 3 is a common factor. I can factor that out. And then the numbers themselves, I have 6x here. See, 3 times 2x is 6x. I have -12 here. So I can take a 6 or a -6 out as well. So you would do that, and then you'd be left with a sum of whatever's left over. Okay, so that's kind of next. I think this is good enough chunk for now, just to understand the chain rule. Okay, any questions about the chain rule right now so far? Scanning the classroom. So example 7, as you can see, if h is a differentiable function. So just remember that the functions that are involved here do have to be differentiable for us to have a solution. Now, for most of these questions, it's going to be assumed, or it will be stated like this, that all functions are differentiable. Okay? You don't know what the functions are. They're just h of x, or f of x, or g of x. So you're going to assume that they're differentiable, right? If you get a question on the test saying, find the derivative of this function, f of x, or f of g of x, blah, 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 show me that. And you say, we're not sure that f of x and g of x are differentiable, therefore I cannot do this question. Don't do that. We'll assume that they're differentiable, unless you're told otherwise, okay? But anyways, this kind of question here would be like, okay, do you see the outside function? Yeah, it's this thing cubed. The inside function is h of x. So we'll take the derivative of the thing cubed, and we will multiply by the derivative of h prime. So that's where you get 3, well, it should be 3h of x cubed times x squared, which I don't like how they've done this. Okay, that's b. A, do I like how they've done this? 3, oh, here we go, 3 times h of x squared, that's the derivative of the first part, times h prime of x. Okay, the derivative of this one. All right, so you might get a question like this as well. So we won't do this one right now, but watch what happens here. The outside function, look at, we have square root on the outside. Inside, I have x plus root x squared plus 1. That's the second layer. The third layer would be the root inside. The fourth layer would be x squared plus 1. So there are multiple layers here. Outside, work your way inside, work your way inside, drill down. Now technically, you stop when x, or your variable, is the innermost layer. That's technically when you stop. And what do I mean by that? Well, again, I don't want to confuse you, but watch this. I could have done one more layer of differentiation here. I said, hey, the outside layer is this blob to the power of 8. Inside layer is x squared minus x plus 2. There is another layer. That layer is x itself. So what's the derivative of x? 1. So technically, you can multiply by 1, taking the derivative of the innermost layer, which is your actual variable. We don't do that, though. We just take the base expression that contains the variable, and that's how we kind of leave it. Okay, but do you understand? With respect to x, it means you drill all the way down until you get down to x. But the derivative of x is just times 1, so we don't really ever show that. That makes sense, right? So over here, I would do times 1, because what's the derivative of x times 1? Over here, times 1. Big deal. Alrighty. Okay, where's your assignment here? Oh, look at this. Oh, love it. Okay, so here's all the differentiation rules. Stewart Calculus text, the first course. Love it. So you want to check this one out in your textbook. Love it. All the rules right there in one compact little package for you. Beauty. Constant rule, nice. Constant multiple rule, beauty. Sum difference rule, love it. Product rule, one of my favorites. Quotient rule, a little ugly but effective. Chain rule, amazing. Power rule, pretty basic. Chain and power rules, look at that, it's got their own special line there. So this is what we learned here today. Chain rule, everybody's feeling good about it. Everybody loves calculus. Chain rule is easy. You can teach that to your, go teach it to your mom and dad at home. Say, hey, guess what I learned today? Have a seat. They'll be like, no! That's what they'll do. Don't do it. All right.